Okay, now
Yes.
it started. Okay, so I'm Abhishek, and today I want to present on this paper, AnyDoor. It is a zero-shot object-level image customization, where we are trying to present a very niche method for customizing the image by using teleporting objects into new scenes at a specific location, which is defined by the user itself. Like we have an image, a 2D image, and on that 2D image, we want to place an object. Okay, the object is given by user, and we want that object needs to be placed at a scene uh, odometrically and geometrically correct. Okay, and this there has been a lot of research going on in this area, and today we are here discussing about AnyDoor. Okay, it is a diffusion-based image generator designed to perform object-level customization without any parameter tuning. Like one shot, it will be able to do it if we use the pretend model. Okay, now what is happening in this, right? We know about what is our goal, right? If we want to provide uh, an approach or a solution for which object-level image editing is possible, right? Where objects can be seamlessly integrated into a new environment with desired adjustment in position, orientation, and shape. Now, all the traditional image editing techniques, what we have seen, right, they are able to place the object, like we know this inpainting methods, and there are certain other methods which is using combination of, clip, which is another texture model, and with diffusion models. Yes, they are using diffusion as the base generator, but the problem is it is unable to take care of the lighting effect, or it is failing with the odometry or the geometry. Okay, but the key in AnyDoor is it allows for object customization without requiring fine tuning, and with it is taking care of uh, key features like lights, the position, and all those things are taken care. Okay, let's deep dive. What is happening? Okay, so here what we're trying to do is, let's say this is our target object. Okay, and let's say we have a scene. This is just four images. Consider at let's take example of only this image, because in a real world scenario we will put an object and put an scene. That's it. Okay. Now what is happening? This object we want to place at this position, and how we will place it. Okay. This needs to be exactly this way. Okay. Now this is looking somewhere front, but here we want it to look at a side view, right? How we can achieve it? Let's go step by step. Now, throughout the session, I will use this fire symbol. Consider it as a trainable model. The parameters are still getting learned. And the snowflake symbol, for which we are telling that the model is freezed. Okay, here we are learning the parameters, but here parameters are just freezed. Okay, now what are we trying to do? Let's go step by step. Okay, the first one is segmented. Okay, you can see this green box. So throughout the session, I will use this green box to segment, like where are we looking, what part we are discussing at the moment. Okay, now this image is going
And
through
Abhishek,
an image. Yeah.
basically here, this kind of approach is helpful for what? Like, what are the applications? Like, is it virtual try-on as well as a synthetic data generator, right? That's what.
Okay. Yeah. I thought that I will discuss about the application at the end, but the applications what we can have is to create synthetic data. Okay. We can use this type of applications like to create scenes. Let's say we are working on a very big machinery plant. Where there is burners in a petrochemical plant. We want to detect fire and smoke. We want to detect activity if someone has got fainted. But how we will create data where fire is there and persons are there, okay, around that? How we will create, how we will detect a person is nearby to a fire area? We can't ask a person to go there, okay, we will record a scene, right? We have to create synthetic data which looks real. That is one
Hmm.
of the application we can create synthetic data. Secondly, virtual try on. Okay, we can put we can take a picture where where we have t-shirt, and that t-shirt we want to place on a person. Okay, and that should fit to that person. Okay, so that is something also we can try out with this AnyDoor. Okay, and
So
we can also
in a way, we can try to have a different background. Suppose if a person, if we want to keep a person in a different background, also that can also be done in a very photorealistic way, right? By using this kind of thing.
yes. That could also be done because this particular architecture they are claiming that we are taking care of the lighting effects as well. Now they can create shadow as well. Okay, if there is some specific amount of light, we will see at the end of the slides. I have generated a couple of results where I put an object and it is creating shadow as well. Okay, that is also taking care.
Yes, yes.
Okay, so we were discussing about the segmenter. What is happening? The first step is we have an object. This is our reference object. This we want to place at a scene. Let's forget all this area. Let's only focus on this part. Okay. Now, this is just a pre-trained model. We can use any object drop or let's say, for example, segment anything model, okay, which is released by Meta and it is highly famous for doing segmentation. You don't need to train your any unit model from scratch. So we want to segment the background, okay, and we want this object to get preserved because we don't want to introduce any noise in the reference object. Reference object should just be the reference object. Okay, here you can
So
see
it,
we have segmented out.
so is it this segmenter has to be suppose if there are multiple objects are there in the input image.
Okay,
So
okay.
is it possible for us to pick object of interest in that one in that target?
Yeah, exactly. Now, this is an object. It's better to keep it as one object only
Okay,
because at a time we want to place one because we want to place something, right? So you are
correct.
a person, you want to place. You can't place two objects at a time. So that's why let's do even AI also. Let's limit it to one object at a time.
So as of now, this one is restricted to one object place, right?
Yes.
Oh,
Okay, we have segmented the object. What next? Now, after we have segmented, it is going through ID extractor. Okay. Now, what is this ID extractor? Now, this ID extractor, if I go to the next slide, okay, we have segmented the object and it is going through ID extractor. Now, let's understand this ID extractor as two parts. One is our self-supervised encoder, and another one is nothing but a multi-layer perceptron. Okay. Now, the output of the self-supervised encoder, which is for this particular image, that output we are feeding to a simple multi-layer perceptron. Okay, we will come that why are we doing that, but now understand that let's say we are feeding this input object into a pre-trained self-supervised encoder. Now, what
so
is that
what is
self-supervised encoder?
so here? What is the major role of ID extractor, and what kind of attribute it has to pick up out of that object?
Okay, okay. So what are we trying to do if I go to this particular whole architecture, right? At the end, this entire part is a diffusion model. It's a
Hmm,
pre-trained text to image diffusion model
hmm,
where we are giving a prompt and it will generate an image. That we know
hmm,
that's what happens in a diffusion model. We will provide a prompt and it will generate an image. Now that
hmm,
prompt we don't want guided, right? We don't have any text. We want this object. Now what we want to do is we want to come up with a mechanism where
hmm,
these features are represented in such a way that the diffusion model is learning those prompts, and those prompt won't be text. We will
hmm.
fit this image as the same dimension as that text, and that we will achieve via this encoder and multi-layer perceptron.
Okay, so it is in the text prompt space that unit can understand, that diffusion model can understand, right? That's what ID
Exactly. This
extractor
is
projects the that
exactly
object of interest.
exactly. This
Oh,
object is represented in such a way which is similar dimension as the text prompt. Okay, the dimension length what we have, and that we are feeding through this diffusion model. We will uncover this in the later part. Let's understand that at the end, it is a text to image diffusion model, but we don't have text. We want to represent that into terms of text, and that text, how we gonna represent, let's deep dive into it. And does it sound good? Shall we move?
yeah. Please go ahead. Yeah, yeah.
Okay. So, yeah, in my session start, I mentioned that this particular model is taking care of the feature representation in such a way that this model is able to preserve the features much better than the other research stuffs that we see in India. What different it is doing? It is using a DINO V2 model, which is released by Meta. It is a self-supervised vision model. Okay, and this comes from Facebook AI research, focuses on learning image representation without the need of labeled data. It builds upon the original DINO head. We will deep dive what is that DINO approach. Okay, and it improves the ability of the vision transformers to learn high quality features from this images what we are feeding into the model in an unsupervised manner. We feed the images, it tries to learn the features, okay, in a much more different way of extraction. What
So
is the
is it
objective of this data?
DINO V2? Is
Yeah.
it better than the clip visual representation?
Yes. Because clip, what is happening that we are providing an image, okay, a prompt, and it is generating an image. Right? I mean, we have text to image this combination, right? And we are trying to minimize their distance. But what is happening? It is not representing. I mean, here the major reason is we want to understand the features in a more granular level. Okay, and
Okay.
then clip for every text you will have that same feature representation only.
So it's can I put it in this way? Like, is it a clip is like a more of semantic thing, but when it comes to DINO V2, is there more localized information also we can extract? Is that the way?
Yes. We can tell that clip is more, semantic representation, and Dynavido is more image to image representation. Okay. Now, what is happening in a clip is, it is more related to the learning the natural language. Okay. It creates a joint embedding, right, in clip.
Hmm.
That is what we have seen. But what happens in a Dino of V2, right? It
Hmm.
uses primarily a vision transformer, okay, and its backbone architecture, and it
Hmm.
self-supervised learns. We have models which is learning within the model, okay, and the self-supervised learn, no labeled data using distillation technique, what we know traditionally as teacher-student, okay, where the model learns to predict its own features.
Suppose
But in
if you look
clip,
into
what is
this diagram,
happening?
if
Yeah.
sorry, please don't mind. So if you look into this, whatever the diagrams are there in the slide, right? So
Mhm.
those are highlighted and multicolored representations are there, right? So are those the
Yeah.
output of the self-supervised encoder or the output of the linear representation as well?
It is output of the self-supervised encoder. Now we are
Okay.
here only. Now we are still
Okay.
here. I
So
haven't
these
reached it
colorful
yet.
representations are the output of the self-supervised encoder, right?
Exactly.
Okay. So that means self-supervised encoder is able to capture that content, that object of interest content, right?
Yes.
So much more because it is some
Ex-
kind of a heat map. So which is able to
Exactly.
capture the exact object shape and contours properly, right?
Correct. Because it extracts very high quality features within the model from itself. Okay.
So
It learns within the model because
if we use a clip over there, so you say that like we cannot have that much fine representation. Is that the
we
word?
cannot have that much fine representation. Yeah.
Okay. So do we have those any sort of learned representations out of a clip to show the difference between the dyno and the clip?
Okay, so clip is, it is more better where we have both visual and textual data, but here we don't have any text for clip, you need to provide some prompt. Yes, you can feed image features in a text level to the clip, okay, but Dino V2 within the image itself, we can extract very high quality image features without any labels.
But in
So
the
that's
clip
why,
also we can,
this,
but in the clip we can take visual encoder, right? Which is already having representations that aligns with the text, but we don't want text here. That's what you're saying, right?
exactly, clip we can still use. This will still work with clip. But
Okay.
clip will not generate more and more features as we are seeing within here, right? It can create more and more representation of the elephant. That is something clip can't do,
Okay. Okay. Please go ahead. Yeah.
right? Okay. Yeah, what is the more objective of this DINO V2 is we want to represent and generate more and more features. Okay, that's the core objective, and this DINO V2 is generating such large amount of data that it is taking care of the images, the lighting conditions as it is generating more and more feature representation. Okay, let's deep dive how it is working. Now we know a vision transformer network, right? Now this vision transformer network, we know we feed an image, okay, and that image goes through this linear projection fashion plexus, and then it goes through our encoder, and then we have a final MLP head, and then we classify, right, whether it is a dog or whether it is a cat. Now this MLP head, this the same VIT network, what we are already aware of, is represented this head with a DINO head. Okay. Now what does this happen? This DINO head is nothing. It is still the same thing. It's just that how we are representing the data. Okay. It is still that MLP. Now, what is happening in our DINO head is, and this particular DINO, right, we will change it into a different architecture. Let's see what we are we trying to do. Now this DINO augment, okay, it uses some better way of representing the data where we have this big input image and we take couple of global crops, which is just two half of the image, let's say, or two half this way. And then we have some local crops, some small patches of this image. And then what we do is this global crop, we feed into a teacher model, okay? And this local crops, we feed into a student model. Teacher model is freezed. Student model is trainable. Okay. Now, what are we trying to do is we are trying to minimize the loss. Okay. This particular concept, what we are trying to do is we are trying to learn this representation, and this student is trying to mimic this teacher. And this we are common with a technique called knowledge distillation. Okay. This model is freeze, this model is trained. So we have this minus P2, right? So that's why we have this freeze, and we are trying to minimize their loss. We are trying to minimize the output coming from the student model and the teacher model. Okay, and we are checking, okay, how is the representation of the loss. Okay, so in practice, in DINO, there are many such distillation models which are taken care and then they are averaged out.
So
After
if you
this,
like
it could
in a way the traditional VAT and the DINO, right? So what the DINO kind of training is bringing is it is kind of training the student, like distilling the knowledge of a teacher into a student, but at the same time it is trying to give more localized information by the DINO augmentation, right? Because it is trying to
exactly,
create a
Praveen.
patches and feeding to a student as well.
Exactly,
So
Praveen.
it is making the student to learn what teacher already has learned, but from a patches, from a localized information. So that's how the student
Exactly.
becomes much more stronger in extracting those localized and details, right, in the images.
Exactly, Praveen. Yeah.
Right. Yeah, please go ahead.
Okay. Now we have reached till here, okay? And the output, as I mentioned, it is going through a multi-layer perceptron, and the output of that multi-layer perceptron is the same dimension as we have in our diffusion model, which is the text prompt. We will uncover this part. Let's understand this is just a black box, this particular thing. We will uncover that. Now, this object is also going through some high pass filters. Okay, it is also going through some high pass filters. We will see what are those high pass filters, and it is also, oh, we are taking the scene image, the scene where we want to place the object, and this feature representation, and we are trying to stitch. So what has happened? This object I have represented some technique I have used to represent the feature, and this I just paste it. That geometry odometry I will take care. But right now I'm just pasting. I'm just pasting it over here on the location that I want to get. Okay, so just concatenation. Don't understand this as four images. This is just one single image only. So for this image, for this scene, we are trying to place it. And
So
this
for
feature
just for the
representation,
example, say there are four sections are there, but it is image by image only, right? Single image.
it is image by image, single image at a time, single image only.
So here, what could be the reason to consider the high frequency map from the object of interest? Because
It
the
is
object of
for
interest is
the
available.
shape. Yes, yes, we want to control the shape. So we want to understand better low-level feature representation in terms of edges and representing the object that we have in the object of interest we have.
Okay, so we wanted to have that shape contour of an object of interest.
Yes, shape contour. Yeah, yeah.
Oh, yes.
Okay. Now this high frequency feature map is represented in such a way that we have an input image, okay, and we convert it to a grayscale image, and we do a linear operation on this K subscript H, which is your horizontal Sobel filter, and we have K subscript V, which is your vertical Sobel filter, okay, and we do another linear operation of addition of this image with this filter and this image with this filter, okay, and then we are doing, and this, what is this linear operation? If I try to uncover this cross, what you see, it is referring to convolution. And outside, what we are doing to is this dot, what you are seeing, it is a Hadamard product, okay,
So
with
in
the
a way,
original
that is
input image
element-wise
type,
multiplication only, right?
element-wise multiplication. And then we apply irradiant mask to filter out the information near the contours. So let's say this was the image, and we did this operation, and this is what the output we are trying to get. Okay. This kind of representation we are getting.
Okay.
There's example 1, 2, 3 images. This 1, 2, 3, 6 images, and this is something representation we are getting.
Okay. Okay.
Okay. Now you are saying that okay, we have reached it to the level. At this level, we have our prompts, which are nothing but image prompts and converted into text length. And this particular thing, we have our image. Okay, we have pasted. We have pasted this thing on the target location. Now that we are feeding into a diffusion model, what happens in a diffusion model? We have a prompt, we just provide the prompt and it generates an image, right? But right now, what are we trying to do is, in any diffusion model, when we provide a prompt, noisy image is generated, and at every iteration, it tries to denoise this image with respect to this prompt, and then we get a very high quality representation of a image, like here, a golden retriever dog wearing a blue checkered Britain and red dotted turtleneck. Okay, this is something that we get from a diffusion model. Now that is something we are trying to extract. We have a prompt which are nothing but image features, and this noisy patch we have created from our diffusion model internals. Okay. Now this is nothing. This diffusion model, why it worked? It worked because we used ControlNet. Okay. Now this ControlNet is very similar to stable diffusion based diffusion model. But what happens in ControlNet, right? So ControlNet, in terms of that, it is using the same encoder of our stable diffusion. But here, what is happening? We have encoder. Okay, this is our encoder, and then we have this middle block. Okay, and then we have the skip connected, something like skip connection injected into this encoder. Okay, this is trainable, and this is freezed. Okay, so what is happening? Whatever output we are getting, it is getting injected over here. So it is the same thing what we see if we see this particular architecture, right? This detail extractor, this trainable is nothing. This entire thing is control net, and this detail extractor is our control net trainable model only. Okay, so this gets injects over here, and its entire process is nothing but control net. Okay, this itself is control net. Okay, and control net is very efficient since it locks the parameters which are frozen, and no gradient computation is required in the originally locked encoder for fine tuning. Okay. Uh, After we have trained, right, I have come to this result section, and this is something. This was the original input image. This was my reference object, and this reference object, I want to place it over here. Okay, we create segmentation mask for both reference object and the background scene where we want to place. This is the mask. Here we create a segmentation because there could be noise if we put the entire image. Because when we capture an object, there could be any background, and background segmentation might not remove the entire thing. That's why we segment this area. Okay, as we discussed in the segment anything model approach. Can you see the output? This created a shadow, right? There was no shadow initially. When we create the segmentation mask as well, right? We don't take this into consideration, the shadow. But the shadow is automatically created. Can you see? There was nothing. This is looks something different. A new shadow is created over here. okay, based on the lighting condition, based on the features. That is why it is powerful. That is why AnyDoor is powerful. So coming to the conclusion, this is a very novel approach, what we have seen in the research industry, and it was presented in CVPR 2024. Okay, the method's ability to work without parameter tuning and its zero-shot capability makes it highly adaptable and user-friendly. There's challenges, the need for more detailed training data and advanced decoders to handle integrated data remains a challenge. So it is a very innovative approach for image object level image customization, and that it did push boundary up to many extent. Any questions, brother?
Yeah, looks good. Yeah, no questions. Yeah.
Okay.
And what are the applications? Did you get a chance to explore, like other than virtual try-on and synthetic data generation?
Yes, I just saw one for object insertion, but there are multiple other applications like where we can put an object into put an shirt into one person. There are many such applications, but I have just incorporated one such example where we are putting an object, many things. Any object we can put at any scene. The shirt is also an object that we are trying to put on a person. Same
Okay.
approach, but we will follow.
Okay.
Same
So
approach we will follow.
can you go to the previous slides? Like I want to understand two aspects. One is the ControlNet one, and another one is the high frequency map after stitching.
Okay, okay.
So can you
One
go to
second.
that high frequency map after like stitching?
Yeah.
Yeah, yeah. Okay, previous slide, previous or forward, yes, forward maybe, yeah, because there are no slide numbers, right? So that's why I'm getting.
Okay, okay. Is this one?
Here, this one. So here,
Okay.
see, object of interest is there, right? Like, why do we want to? There is a concatenate collage and shape mask. So how
Mm-hmm.
this is finally, what is the output of this block? Because collage is basically the high frequency map of the object of interest, right?
Yeah, yeah.
So and concat
Okay.
and here wow, what is this basically? Here this will be
Yeah. Let me try to explain. Now, initially, this high frequency map image what we had, right?
hmm,
On this location, we just try to paste it, but the
hmm.
shape was not taken into care. So that thing is what we are concatenating, that matrix.
So what is the output like out of this one? So both the high collage maps is separately, shape marks separately, or also only one?
No. This representation what we have, right? This
Hmm,
gets so this particular thing is pasted over here, right? It is a stack. Okay, this is pasted over here,
hmm,
and this is
hmm.
also stacked into this particular array. And then together we are feeding it into the diffusion model.
So both the mask as well as the collage map, both are fed, right?
Exactly.
So they are concatenated. Like now it
Yeah,
becomes, suppose the collage map is one channel. So shape mask is now the output of this whole process is a two channel, right? One channel is a
yeah,
binary
yeah,
mask, one channel is a collage.
yeah, yeah, yeah.
Okay, okay. Okay. And did you try out, suppose if there is no collage mask and if you try only the shape mask, so what would happen? Because at the end of the
No,
day,
this is
uh,
we are internally taking care. I didn't try because this was the direct approach wherein the architecture itself we are taking care of this high pass filter, and this high pass filters why they're important, right? Because it helps extract very high frequency components, and this image filters help, yeah, to isolate high frequency components, and it helps, the Sobel operation of the other filters what we have gradient based techniques, right? It highlights the edges. So that's why we do use, this representation did help. I didn't remove this particular step
for
because
example,
this is just a pre-processing time.
yeah, based on your understanding, right? Suppose if we avoid, like, just it's a hypothetically, I'm asking. Suppose if we feed only the shape mask, and
Uh-huh.
if we feed from the bottom side, right? So if we
Okay.
take the ID extractor output side, that is ID tokens, right? So what would happen?
Uh-huh.
Like because the mask is coming from the top side, and the object of interest tokens, semantic information and localized information is coming from the ID extractor, and both are
Yeah.
controlling in the diffusion model, right? So
Yeah.
are they not going to be enough? Why do we need this high pass filter? In what way it's going to bring? Like,
It is more about representing the features, right? This high frequency component. The purpose is to extract and emphasize this high frequency component from an image. It does provide a very detailed representation of the object's fine features. It's more of representing the feature only,
hmm.
because it does help in object relocation and shape customization. Because if we want to custom the shape, right? I have a person skeleton and I want to try to look that person in a different way. Now right now it is looking too straight, but how I will change the pose? This edge help.
But where we are passing this scene and location, because I in the collage and the shape mask, I don't see with this context anyway, right? How
Okay,
it is.
this scene and location, this is nothing but a background mask only, and this together we are trying to convert and feed into the diffusion.
So we are going to concatenate the scene also location with the shape mask as well, collage, shape mask, and all those stuff.
This is just an input representation. Initially, it is not way. This is only for the visualization. This is where we are taking care of the mask. Here we are
Okay.
telling we have scene and mask as input, but
So
here we are
somehow,
actually contacted.
we have to ensure that the scene and location also fed to the model, right? Otherwise, the
Yeah,
model
obviously.
never know on what context it has to paste upon.
Yeah. And location is up to the user.
Location is up to the user, but after the collage and shape mask, if you go to the original architecture, so detailed extractor is there, right? So out of that
Yeah.
one, the scene and location related information should also be fed, right?
Could you repeat your question?
So the detail extractor, if you go to the architecture,
Yeah.
here detail extractor output, right? Detail maps is there, right?
Yeah.
In the detail map, so basically it has to see shape mask as well as the collage as well as the scene plus local information, because it requires in what
Yes.
orientation
Yes. Yes.
it has to place, and what is the context, and what is the object details.
Exactly.
So the detail
Exactly.
map output, detail maps, right? It consists of all these three informations, right?
Absolutely.
Okay. Yeah, another one is, can you go to that ControlNet architecture?
Yeah.
ControlNet. Yeah. There.
Yeah.
Yeah.
Let me go here.
So here, can you be a bit elaborate? Like the stable diffusion is, they're not going to train it, right? It is a pre-trained one.
Yeah.
So the train, like in what they are going to train here, basically in the whole architecture thing, right? So are they going to
Yeah.
train end to end, including the diffusion model, or only the ControlNet architecture is going to be trained?
This
Oh, they
itself
mentioned.
is
Okay. Yeah.
yeah.
Sorry, I
Yeah,
missed it.
yeah, the
Yeah.
control
Double
it. So
copy.
this is only trainable. This is only
Ah.
trainable.
Okay. Got it.
And that's why
Okay.
we can do it with two A100 GPUs or something. It doesn't shoot up much memory.
Right. Oh. This is good. Good, Abhishek. Thank you so much. Yeah. Great.
Thank you, Praveen. Bye.